Hey guys, my name is Frank. This is the Poth on Programming video log, and today I'm going to be doing part 3 of my 4-part series on tile types, which is just tile-based collision detection shapes. And as you can see, I have all these cool shapes on the screen that I can interact with, and they all do different stuff. But today's tutorial, or just video, is going to be on slope tiles. So, I'm just going to go over the narrow phase slope top collision function. All these use this function. This one uses this function. These use this function. This one actually does not. It's a much simpler function, and I'm actually going to go over this one first. So if I come down here, go over these curved tiles, as you can see, I'm climbing up this slope tile, and you probably wouldn't want to collide with a slope tile like this. You don't want the corners to collide. You want the center to collide, but it's pretty simple to switch that over. It's just I wanted to be thorough and go over the corners and just talk about the collision code. Doesn't really matter that having your sprite in this hitbox would look stupid right here because he'd be floating above the slope tile. You want the center point here to be here, basically. So anyway, I'm just going to get into the collision method for this, and then I'm going to talk about this more complicated collision method that handles narrow phase with these platform slope tiles. So actually, I don't have a specific narrow phase function that I can reuse for this one. I just have it built into the routing function. I have it built right into the routing function. So I'm going to find the routing function for this one. Actually, I'm going to go see which one this even is. I think it's tile 8 in my tiles here. So I'm going to go to routing function 8. And there we have it. This is the collision method that handles collision for this tile. So this is an interesting case because it actually just, all it does is push the object up out of it. So if I come over here to this unsloped side, you can see that when I enter into it, it just pops me right up to the top, because all this tile knows is that if this yellow square is below the slope, I need to move it up on the y-axis until it is no longer in collision with this tile. So it works great if you're going to put it in, say, a corner. Like if I move this guy over to here, it would work perfectly fine. And you should use this. You should use this type of tile. They don't all have to be platform tiles. They can very easily be this type of tile. And I'd say the code is a lot more efficient. So use tiles wisely and choose the right tile for the application you're going to use it in your game. So now I'm actually going to talk about the code here instead of going on about that stuff. So the first thing that I've got to do inside of my narrow phase is determine where the X is, because if you remember back to geometry, that formula for the slope of a line, y equals mx plus b. So if you break that down, y is just going to be the top of our tile. M is going to be the slope of our tile. In this case, the slope is -1. As you can see here, I've got -1 for the slope. X is going to be either the left or the right corner of our player. In this case, it's going to be the right corner. It's the only corner we can collide with this tile on. Actually, I'm going to do something interesting here, and I'm going to make this the center of the tile by multiplying the object's width by 0.5. I'm going to save that. I'm going to come in and start this over. And that looks a lot better, doesn't it? Doesn't that look a lot better? And it's as simple as changing barely a fraction of a line of code here. So I can do that. So we just have to get that slope form of y equals mx plus b. So for this tile, first thing we do is we get x, and that's going to be the center of the object on its x-axis. And we're going to subtract the left side of our tile space because we want our origin to be relative to the tile space. So our origin is going to be up here, which is the top left corner of the tile space, not the player, but the top left corner of the tile space, which is right here. We want that to be our origin when doing this calculation here. So we get x on the object, which is just the x starting from 0 here. It's going to be right here. To get y, we use the y equals mx plus b formula. So we have y, which is our top. M is going to be -1 because the slope is -1 rise over +1 run. So -1 rise, +1 run. We multiply that by x, which is our current x value here. And then we add b, which is just the y-intercept. So the y-intercept in this case is going to be the bottom of our tile, because where this line intersects x equals 0, I think that's where it's supposed to be, is at y equals 0, or y equals tile size, excuse me, which is 16. So if we start our origin here at 0, 0, this is going to be 16. So b is going to be equal to all of this, which is tile size, which is 16, plus our row times tile size, which is going to bring us all the way down here. So row times tile size brings us to the top of this tile space. Adding tile size brings us to the bottom of the tile space. So we basically just duplicate that form. Y equals mx plus b. So really simple. And now you can say you actually used geometry. They told you were going to need it in life, and now you're actually using it. How about that? So then we have a special case that we need to cover. If I comment this out here, I'm just going to show you the slope collision, and that's it. So I'm going to comment out the special case and just go over the slope first. I'm going to refresh this, come back down. Now, as you can see, we have something a little weird. And that's just because we're no longer accounting for what happens if we're standing on top of the tile and there's no more slope over here. We're just moving the object up according to this never-ending line here. So imagine there's just a never-ending line that just goes through the edges of this green slope tile, or out past them. As we move up out of the tile space and we fall into it, we're still detecting that we're in collision with that line, but the object is moved up out of the tile space, out of collision with it, and then it falls back down until it is in collision. That's why we have this little jumping motion here. So what we need to check for is simply if our object's y position plus the object's height, so basically if the bottom of the object is greater than the top of the tile, and the top is basically the spot on the slope that is directly under the center of our object. So we just check to see if the bottom of this object is lower than the top of this slope tile where it's relative to the center of the object on the x-axis. And we just do basic collision resolution. We set jumping to false so we can jump again. We set y velocity equal to 0, which stops gravity from building up in our y velocity and having a huge y velocity. And we set y equal to the top, which is right here, minus the object's height, which brings us here, and we subtract this slight offset. I'm not going to talk about the slight offset. I talked about it a lot in the last 2 tutorials. Particularly, I know for sure I talked about it in part 2 of this series, so check that out if you want to know about the y offset. I can take this away and it doesn't really affect this, but I'm just keeping it in there for consistency. So that's basically how to collide with the slope. And to clean things up, to get rid of this behavior here where you're kind of jumping on top of the tile when you're on the edge, we just add in this special case code here. So I'm going to comment this back in and show you the functionality and then the code that makes it work. So now we have that nice kind of, we're actually sitting on the edge of the tile. And that's how you want it. So why is that happening? So basically we just test the condition if the center x position of our object is greater than 16 in the tile space. So 16 or tile size. Remember, origin is at 0, 0 right here. And if we add 16 to that, we come over here. So if our center x position of our object is greater than this, which it is in this case, we're going to run this code instead of this code. And all this code does is set it up to sit on the very top of the tile space rather than the slope. So it basically goes back to basic flat surface collision response. And we set jumping to false, we set y velocity to 0, and we basically just set the object's y position up to equal the row times the tile size, which will bring us right to the top of the tile. And then we subtract object that height and that offset again. So really simple. So this is basically a very simple slope tile narrow phase collision function. Now I'm going to get into the platform slope tiles. And the reason they're platform is because you can jump up through the bottom. So if I jump up through the bottom here, I can walk around beneath this and I could jump up through it. But as soon as I'm on top of it, I can't get back through, which is kind of cool. I mean, you could find applications for this. The main reason I do this is because I can use this as part of a composite tile. Right here, this composite slope tile is really cool because you can't enter into it from any direction. And it's a slope tile. So if you want this cool shape in your game, you can have it with this system. So now I'm going to go up to the, or down rather, to the actual narrow phase function that is used in all of these top slope tiles. And that function is collide slope top, and it is rather beastly. So the approach I use with this is actually a vector math approach, because if you remember the last tutorial or the last video in this series where I was talking about these tiles and platform tiles, when you collide with these, the way you detect collision is by checking to see if you are moving through the top. So basically, you have to have your current point below the tile top and your old point above the tile top to prove that your vector is actually intersecting the top of the tile or the flat line. So you basically just have to do line intersection here. So we have the line for the slope already, and then we just have to get a line for the movement vector of the player. So say I'm falling down and I'm landing on this tile. The start of my movement vector is going to be here, and the end point is going to be on the other side of this line if I have a collision. And if not, I don't have a collision. So if it starts here and it moves over here, I don't have a collision because there's no intersection. We're not going to do real line-to-line intersection here. We're not going to do that math. All we're going to do is some basic vector math that just checks to see if a point is on one side of the line. So we're going to check to see if the old point is on one side of the line and if the new point or the current point is on the other side of the line. And if it is, we know that we've passed through the line. And it's an infinite line, by the way, so we just are passing through. You're either on one side of the line or the other. Doesn't matter if you're to the left or to the right. All that matters is the previous point on one side and the current point on the other. So all of these values right here are basically just setting up our different vectors. First, we have to get the origin, and as I was explaining before, actually I'm going to get to a different tile space. Actually, I guess this is pretty good. I'm going to move over here. As I was saying before about the origin, it's in the top left corner of the tile space. So if I'm going to collide with this tile here, the origin is going to be about here. This is the top left corner of the tile space. So I just get the origin X and origin Y for that top left corner. Now I have a reference point to calculate all my other vectors, like the vector of this line and the vector of the previous to current location of whatever point on my player character that I'm going to do. So then we get current X and current Y, and that is just going to be the current X and Y position of whatever side or whatever corner of the player that we're going to be using for the X value. In the formula, Y equals mx plus b. So we're just going to get this corner. In this case, it's the bottom right corner. So these functions do that. Current X just checks to see which direction the slope is facing. If the slope is negative, like the tile I'm standing on, we're going to use the right bottom corner. If the slope is positive, like this tile over here, we're going to use the left bottom corner. And as you can see, I'm colliding on the left bottom corner here and the right bottom corner here. So that's what this little condensed if statement is doing. It's basically just saying, is the slope less than 0? If it is, then use the right corner. And if it's not, then use the left corner. And of course, subtract that origin X so we can have everything relative to the top left corner of our tile space. Then we have to do the same thing for the old position. And basically just the same exact thing, just replacing the current X and Y with the old X and Y. And then we have to get the cross products. So cross product is basically just a vector operation. If you've ever done dot product, you're probably more familiar with that one. Cross product can be used to determine if a point is on a certain side of a line, or if a vector is on a certain side of another vector. And that's basically what we're doing here. So we are saying is current X And well, the formula for getting cross product in 2D, it's really a 3D operation, but in 2D, you would do vector 1.x multiplied by vector 2.y minus vector 1.y multiplied by vector 2.x. And we don't do vector 2.x because for the vector, we're just using the slope, which is rise over run, if you remember that geometry principle from your classes in high school. I'm just deriving the vector for this sloped line here from the actual slope itself, which is -1 over 1. So it's going up -1 on the y-axis, and it's going over 1 on the x-axis. So that slope is in itself a unit vector. It's not really a unit vector. It's a tiny vector. But if I want to be really true to form here, I would multiply by 1. It's just, why would you ever want to multiply by 1? It's kind of redundant. So I don't. But this is basically just getting the cross product. And I'm not going to get too in-depth on this stuff. Just know that this is a cross product in 2D. And if you use this enough, you'll kind of figure it out. So copy and paste this code into your own project and check it out for sure. Mess around with it. So the current cross product is just the cross product between the slope vector and the current position vector of the object. So say I'm colliding with this, the current side would be down here. So I would have a vector drawn from up here to this point, and I would have a vector drawn for my slope from here up according to the slope. For the previous point, the vector would be on the other side of the slope line. I should have actually drew something up so I could show you guys this. I probably will do a tutorial much later on about vector math, and I'll have a really cool interactive example to show you guys what I'm talking about. But basically, let's just say one vector is pointing over here on this side of the line, and the other vector is pointing over here on this side of the line, and we can use the cross product to determine which side that is on, because the side that's over here is going to be either negative or positive, and the side that's over here is going to be the opposite sign of that other vector. So that brings me to this next part. After I calculate the top, which is basically the same as calculating the top for the other tile down here, you use these if statements, and you use, well, actually, this is a special case. This is the special case for sitting on top of the tile up here. So I'm going to jump right to the slope code, and I'm actually going to comment this out. I'm going to comment out the special case so you guys can just focus on, if I can get the commenting right here, so you guys can focus on just the code that handles the slope itself. I'm going to do that. I'm going to refresh. I'm going to come up here. And now you see I'm falling off, but that doesn't matter. I'm just colliding with the slope. So I take that cross product, and like I said, if it's on one side of the line, it's going to be a certain sign. If it's on the other side, it's going to be another sign. So basically, these just have to be opposite signs. The current cross product represents the vector, the current vector, or the current point on the player being on one side of the line. So if it's less than 1, and it should just be less than 0, but because this isn't a really numbers intensive, JavaScript isn't really big on numbers, rounding errors make it so I have to make this 1 instead of 0. But if it's less than 1, it means we're on this side of the slope. And if it's greater than -1, it means we're on this side. So basically just check to see if the current position of the bottom right corner of my object is on this side of the slope. That's what this code does. And if my old position of the bottom right corner is on the other side of the slope. And if it is, then I'd just do some basic collision response code, the same code that I did for over here, basically. So now I'm going to talk about the special case, and that is when you are resting on top of the tile. It's a lot more complicated. Well, at least it looks more complicated than the one I showed you before. But it's really not too complicated. Basically, it just accounts for both sloping tiles, so slope up and a slope down. So if current x is less than 0, it means that we are, and I'm going to come over here. Actually, I'm just going to talk about this tile. If current x is less than 0, the current X would be the bottom left-hand corner of my object in this case. So if it's less than 0, it's going to look like this. 0 is right here on this tile, and my bottom left-hand side is less than 0. So if that's the case, or if I'm talking about this tile, and this is the case where the bottom right-hand side is greater than 16, which is right here for this tile, then I know I have to collide with the top of the tile and not the slope. So the next thing we need to do after we determine that we need to collide with the top and not the slope is just do basic flat surface platform collision detection. And I'm not going to go over that because I've probably talked about it 20 times in my tutorials, but basically we check to see if one side is below the top, which is at 0 in the tile space, and if the old position is above the top or equal to the top, and if it is, then we just do basic collision response, and that looks the same as all the other collision response code. And finally, we have one final case which looks redundant, but it's actually really important, and it checks to see if we are on one side or the other of the slope. Because there's one tiny condition in here where you first enter the top of the tile, when you first move up on top of the tile, where this code becomes relevant. And it's the reason I put it all the way at the end, so this if statement can early out if these other first conditions are met, and we don't need to check this one. So I'm going to comment this out and show you guys the error case. Or not an error case, but the glitch. It's not even a glitch. It's just math doing what it's supposed to do and me not accounting for it to get the desired result. So do you see that little jump there? Do you see how he kind of hops up? It's kind of hard to see, actually. And I'm pretty sure the character is moving really fast, so the recording software is not capturing everything very nicely. But there's a slight little jump. Just does not look as smooth as it used to. He kind of like hops up when he gets to the top of the tile. And that's because he's still on the slope before he realizes he needs to be on the flat surface of the tile. So it actually pushes him up slightly above the tile, and then he falls back down onto the slope, or onto the top of the tile. So by including this code in there, this little OR statement, we just check to see if we're still on one side or the other of the tile, and it just makes it so much more smooth. So we go from having this functionality where we kind of jump at the top to having this functionality where we just, oh, I forgot to save my file here. But we go to having this nice smooth functionality where we reach the top and we just stay on the top, and it's really nice and smooth. You get none of that jitter in there. So hopefully I did a good job explaining this code here to you. There's some vector math in it. It's a lot more simple than you think. I have all these values in here, these variables, but they're actually not as complicated as they look. It's really just getting everything into the form y equals mx plus b and getting some vectors to test to see if a point is on the left or right side of a sloped line. Go check out 2D cross product on the internet, and you'll see some articles how to find if a point is on one side or the other of a line. You'll find documentation on this, and it's really simple math, and you'll pick up on it really well, a lot better than you will from listening to me talk about it, because really my purpose is just explaining the code that makes it work and not the math so much behind it. Although I did try, so give me that much. The last thing I'm going to talk about for slope tiles is this composite slope tile. And it's actually, I think this is by far the coolest thing here, because it's just a really complex shape that you wouldn't see in a game very often. So I'm going to go up to the routing function that handles this tile. I forget which one it is, actually. I'm going to check in my tile types graphic here. It is 13. So I'm going to come over here, and I'm going to find the routing function for 13. And as you can see, it's got a little bit more than just your basic functions in it. It has some specific tile functions inside of it. So basically this is just a composition of collide slope top, which I just showed you, collide left for the left side, and collide bottom for the bottom side. And also I have to account for the situation where I'm entering into the tile and this has to block me. This bottom right corner of the tile has to block me. So if I take this code out, just like that, and I save, and I refresh, and I try to interact with this tile. Now all of a sudden I can walk right through that right side. But I don't have to worry about the slope because that collide slope top function is taking care of that. Collide left and collide bottom are taken care of by my other functions in the composition here inside of my routing function. I just have to make this special case here for colliding with that point. And you could very well go ahead and make a narrow phase collision method for colliding with the left, right, bottom, top side of a point. I just didn't have need to because this is the only case in which it occurs in this example. So basically all I'm saying is the object less than the right side of this point or the position of this point? And is the top and bottom of my player object above and below the point? Because if it's above, there can't be a collision, and if it's below, there can't be a collision. Oh, I forgot to refresh my page. But if it's between those 2 points, if this point is between the top and the bottom, then I do have a collision with this. So basically it's all the stuff I already talked about, plus this one little specific case for colliding with a point. I'm not really going to go over that too much more than I already did. It's basically, if you've listened to the last 2 or 3 tutorials I did, you already know what's going on. But that is it. That is slope tiles as quickly as I could manage, and I hope you guys got something out of it. The collide slope top function looks a lot more beastly than it really is. It's really just doing some pretty basic math here. I wouldn't use it for every tile. Remember, in game design, you want the simplest solution. You don't want a one-size-fits-all solution. You would rather take a bunch of efficient code blocks and use them than have one really beastly code block that handles everything every time, because I don't need this tile in this bottom corner. I need the horizontal flip of this tile in this corner, because this is overkill for this corner. This tile is a perfect corner tile because all it does is push me up out of it. And I don't need to worry about the other sides, because when I design my level, these other sides are going to be covered by other tiles that I'm not going to be able to get through. So just keep that in mind. Anyway, this has been part 3 of my 4-part series here that I'm doing. The next part is going to cover curve tiles, and that is pretty exciting because I've never actually programmed these before. But look how well they work. It's like going over the McDonald's arches in my mind. That's how I think about it, but I colored them red for some reason. But that's going to be the next tutorial, so stay tuned, and I will see you guys then.